What if a plane could simply climb and reach orbit, accelerate, pitch up, then be in space within 20 minutes? No massive rockets, no dropping stages, no single-use tanks costing hundreds of millions. It sounds like a problem we should have solved long ago. But after 70 years of trying, from experimental spaceplanes to Virgin Galactic's tourist crafts, no winged vehicle has ever reached orbit on its own. Not one. Sure, we have stunning footage, triumphant headlines, billionaires in spacesuits waving at the camera against a backdrop of black sky. But an actual orbital flight by a plane? That's still missing. To understand why, we need to dig into a harsh truth that's usually left out. Air is what keeps a plane flying. It flows around the wings, which have a special shape that creates a pressure difference between the top and the bottom. This difference literally pushes the aircraft upward. That's lift. Remove the air, and the wing becomes nothing more than a useless piece of metal. But that's not the whole story. A conventional airplane's engines also rely on the atmosphere. A jet engine pulls in air, extracts oxygen, uses that oxygen to burn fuel, and then shoots hot gases out the back. Without atmospheric oxygen, the fuel has nothing to burn. No atmosphere, no thrust. In simple terms, a plane depends on air in two ways, through its wings and through its engines. Remember this formula. It's going to be important later. The air runs out. As you climb higher, the atmosphere grows thinner and thinner. At 10,000 meters, the altitude where commercial airliners fly, the air density is already 3 times lower than at sea level. Climb higher and it thins even more. At a certain altitude, there's so little air that wings lose their grip and engines start to suffocate. The airplane hits a ceiling. Not a metaphorical one, a physical limit. But where exactly does the sky end and space begin? The Kármán line marks a notional boundary at 100 kilometers above Earth's surface. The international community accepts this as the edge of outer space. The United States, however, draws that line lower, at 80 kilometers. 20 kilometers might seem like a small difference, yet it causes some to call certain flights space flights, while others do not. This gap will prove significant later on. Here's the big question. For decades, engineers have chased an ideal concept. It's called single stage to orbit, a vehicle that takes off whole, reaches orbit without dropping any parts, and returns intact. No boosters falling away, no disposable fuel tanks. You launch, land, refuel, and take off again, just like an airplane, but in space. So far, no one has built such a craft, not a single one. There have been dozens of projects, billions of dollars spent, the planet's best engineering teams involved, and the result? Zero. Meanwhile, we keep seeing winged vehicles supposedly already flying in space. Something doesn't add up. Why does a problem that seems almost solved remain completely unsolved? And why is it barely talked about? To understand this, we need to go back to the very beginning, to the first pilots who tried to reach the dark sky aboard winged rockets, and to what they found there. The year is 1958. At a factory in Los Angeles, they're assembling a machine unlike any airplane in the world. Its matte black fuselage is coated with an alloy called Inconel, nickel-based, designed to withstand heat up to 1200 degrees Fahrenheit. The wings are short, almost abruptly cut off. The tail looks more like rocket stabilizers than traditional aircraft control surfaces. This is the X-15, an experimental rocket plane destined to become the fastest winged vehicle in history. Over the next 10 years, it will complete nearly 200 flights. 200. Not 2, not 20. 200 trips to the edge of the atmosphere and back. For a program of this scale, that's an enormous trove of data, with every flight a live experiment piloted by a human in the cockpit. Here's the fascinating part. The X-15 couldn't take off on its own. It lacked landing gear for a runway takeoff. It didn't carry enough fuel to climb from the ground to its operational altitude. Engineers at North American Aviation tackled this problem in a way that seems crazy at first and brilliant on second thought. They strapped the rocket plane under the wing of a B-52 bomber. This massive strategic bomber, with a wingspan nearly 60 meters wide, carried the X-15 up to about 14 kilometers, higher than any passenger plane flies. Up there, in the thin air, the rocket plane detached from its carrier and dropped. For a second or two, it was free fall, silent except for the rush of air. Then the pilot fired up the engine. The XLR-99 engine. In my opinion, it stands as one of the most impressive rocket engines of its time, and here's why. It ran for between 80 and 120 seconds, 2 minutes. In those 2 minutes, it burned through about 7 tons of fuel and oxidizer, liquid ammonia and liquid oxygen. 7 tons. That's the weight of 2 large SUVs. It burned away in the time it takes for a kettle to boil. And those 2 minutes changed everything. The best way to understand what happened next is through numbers, because words just can't capture it. A typical passenger jet cruises at about 10,000 meters, or roughly 33,000 feet, flying close to 560 miles per hour. That's the ceiling for normal commercial aviation. Trying to go higher, even just a little, can lead to disaster, and this isn't just theory. In the United States, a crew flying a regional jet on a ferry flight decided to climb to the maximum allowed altitude, 12,497 meters, or 41,000 feet. At that height, the air becomes so thin that both engines failed. The plane went down. Conventional aviation ends somewhere around 12 to 13 kilometers up. What if we build something special? NASA gave it a shot. The experimental drone called Helios was a massive solar-powered flying wing with a wingspan even wider than a Boeing 747. Yet it struggled to reach 30 kilometers in altitude. 30 kilometers. That's the record for any aircraft that stays aloft relying solely on wings and the atmosphere. Beyond that, there's simply no air to breathe, no surface to push against. Now meet the X-15. It hit 6.7 times the speed of sound, 7,274 kilometers per hour. At that velocity, the air rushing over the nose gets white hot, and the skin of the plane heats up to temperatures that would have already melted lead. This stands as the unofficial speed record for a piloted, winged vehicle powered by engines in the atmosphere. And that record still hasn't been broken, not in the 60s, not in the 70s, not even in the 2000s. Not once. But speed tells only half the story. In 2 separate flights, the X-15 climbed beyond 100 kilometers. That's above the Kármán line, the accepted boundary of space we've been talking about. It reached a top altitude of 107 kilometers. Pilot Joe Walker, who flew one of these missions, spent several minutes in a place where the sky shifts from blue to violet, and then to black. Not the black of night. This is the black of space. Stars shine clearly, even in daylight. The Earth's horizon curves beneath him. Below lies a thin blue layer of atmosphere, as fragile as apple skin. The flight controls stop responding. There's no air to push against. The craft switches to tiny gas thrusters, just like a spacecraft, to maneuver. And all of this happens after just 120 seconds of main engine burn. Then, silence. No thrust at all, only a ballistic arc, climbing into the black void, then falling back down, plunged into the rising heat of atmospheric drag. The pilot, cramped inside a tight cockpit, the pressure suit weighing down on their shoulders, the G-forces pinning them to the seat, steers the craft back toward the runway on a dried lake bed in the Mojave Desert. No second approach, no go-around, just one shot. Let's put this ladder together. 10,000 feet marks the ceiling of a commercial airliner. 13,000 feet is already a danger zone where engines can flame out. 30,000 feet is the limit for specialized solar-powered drones. 107,000 feet, that's the X-15. From a typical airplane's ceiling to the rocket plane's record altitude, there's a 10-fold difference. Same wings, same planet, but a completely different machine and a completely different way of flying. Launching from a B-52 wasn't just a workaround, it was a game changer. It saved tons of fuel that would have been burned pushing through the densest, heaviest layer of the atmosphere, the first 14 kilometers. The bomber handled the dirty work, while the rocket plane reserved its precious 120 seconds of thrust for what truly mattered, gaining speed and altitude. The idea proved so effective it stuck. Decades later, a new generation revisited it with entirely different goals. 200 flights, 10 years. A speed record that still stands after more than 60 years. 2 crossings beyond the Kármán line. The X-15 proved something no one had demonstrated before. A human can reach space aboard a winged craft, control it where the air disappears, and return to Earth by gliding down. Not in a capsule under a parachute, but on wings. It felt like the dawn of a new era, the first step towards something that seemed unstoppable. June 21st, 2004, the Mojave Desert in California. The same dry strip of concrete where X-15 pilots once landed. But now, instead of a military machine, a private craft sits on the runway. Small and white, it looks more like an elegant yacht than a rocket plane. This is Spaceship One. In just a few hours, it will climb to 112 kilometers, higher than any piloted winged aircraft in history, even higher than the X-15. A record that stood for 40 years has been broken, not by a government program, not by the military, by a private company. Here's what's truly fascinating. The designer of Spaceship One didn't reinvent the flight concept from scratch. He borrowed an idea that had already proven itself back in the 1950s, the air launch. The White Knight carrier plane lifted the rocket plane to an altitude of 15 kilometers, roughly where commercial jets cruise. At that point, Spaceship One would detach, ignite its engine, and shoot upward. More precisely, it blasted off like a bullet. The logic was the same. Let a conventional airplane handle the heavy, dense lower atmosphere, while the rocket plane burns fuel only to accelerate in the thin air above. In other words, it's the X-15 formula, minus the bomber, plus private investment. But a single record-breaking flight doesn't make an industry. A record proves the technology works. Business proves it's needed. And here, Virgin Galactic steps onto the stage with its craft, VSS Unity. The successor to Spaceship One, it's bigger and more comfortable, with a cabin designed for 6 passengers. Unity carried out tourist flights, real commercial trips that people paid hundreds of thousands of dollars for. In the summer of 2023, the craft completed its final mission. Not because of a crash, not because the technology failed. The program ended as planned. The company was moving on to the next generation of spacecraft. At the same time, entirely different ideas emerged about what could be called near space. Space Perspective offers a radically different approach, a capsule lifted to around 30 kilometers by a giant helium balloon. No rocket engines, no intense G-forces, just sipping tea with a view of the curved horizon. At 30 kilometers, you're above 99% of Earth's atmosphere. The sky turns black, and you can see the Earth's curvature with the naked eye. Visually, it's almost indistinguishable from orbit. But this isn't space yet. You still have about 70 kilometers to go before reaching the Kármán line. For a tourist eager to see the whole planet and snap photos against the backdrop of darkness, the difference between near space and space might matter less than the difference in ticket price. Now, let's dive into a crucial engineering detail that made this whole space tourism story possible. Virgin Galactic Spaceplanes used hybrid rocket engines. That's one part. But the real trick wasn't in the engines. It was in the tail. The system was called feathering, a way to change the angle of the tail surfaces. It works a bit like a badminton shuttlecock. When the craft reaches the highest point of its trajectory and starts to fall back, the tail booms pivot upward nearly 65 degrees. The ship transforms into something like a maple seed. Its broad surface catches the air rushing by and automatically flips the craft belly down. No real-time computer calculations, no active control, pure aerodynamics. In simple terms, the shape of the craft solved a problem that orbital engineers wrestled with for decades: how to re-enter the atmosphere safely without burning up or losing control. At suborbital speeds, it worked brilliantly. The vehicle slowed down, the beams snapped back into place, and then it glided smoothly toward the runway. The familiar finale: wings extended, landing gear down, touchdown, all against the backdrop of the Mojave Desert. Private companies sold tickets, flew tourists, and brought them back safely. Technology born in secret hangars on military bases had transformed into a commercial product. It seemed like all the fundamental challenges were solved. Now it was just a matter of scaling up. But suborbital hops of 100 kilometers are one thing. What if a winged spacecraft needed to reach full orbit, spend a week there, and then return? That called for a vehicle on an entirely different scale. They built that craft, and it flew for 30 years. The Space Shuttle program stands alone in human history as the only system to carry people into orbit aboard winged, reusable vehicles. Not capsules splashing down in the ocean, not single-use rockets burning up after launch, but planes. With wings, landing gear, and a cockpit where a crew of 7 could work for a whole week. From 1981 to 2011, the shuttles launched 135 times. 135 times a 2,000-ton winged machine lifted off from a launch pad in Florida, reached orbit, and returned, gliding down to the runway like a glider. Nothing like it existed before or since. But here's what made this program more than just an engineering showcase. The space shuttles worked. They launched satellites, dozens of them, into orbit. They carried crews to the Russian space station Mir, marking the first time former Cold War rivals flew together in space. They delivered and assembled modules for the International Space Station, a structure the size of a football field hanging nearly 250 miles above Earth. And it was the shuttle, back in 1990, that launched the Hubble Space Telescope into orbit. Even more impressively, it returned 5 times to repair and upgrade the telescope. No capsule or rocket could have done that, approaching a satellite, opening an 18-meter cargo bay, retrieving equipment, swapping out a mirror, and flying back home. It required a true airplane, one with hands, a cargo bay, and a crew capable of spacewalks. Simply put, the shuttle was more than just a mode of transport. It became an orbiting workshop. But the price for these capabilities was terrifying. 2 of the 4 orbiters, Challenger and Columbia, were lost in disasters. 14 astronauts died. That's 14 out of 18 total fatalities in the entire history of crewed spaceflight. Nearly 80% from just one program. Every shuttle launch demanded an incredibly complex system. 2 solid rocket boosters, a massive external fuel tank, and 3 main engines burning liquid hydrogen, all had to work flawlessly. Even the smallest detail, a rubber seal, a piece of insulating foam, could kill the crew, and twice it did. Both superpowers ended up with the same design approach. The Soviet orbital spacecraft Buran used a similar launch concept, vertical liftoff powered by the Energia rocket. Visually, Buran looked almost identical to the American Space Shuttle, but in one way, it surpassed it. In 1988, Buran completed its only spaceflight entirely on autopilot, including landing itself. The spacecraft reached orbit on its own, completed 2 orbits, re-entered the atmosphere, and touched down on the Baikonur runway, all without a pilot. American shuttles never had that capability. A pilot always sat behind the controls. 2 superpowers, 2 continents, 2 independent design bureaus, and one conclusion. An orbital winged spacecraft works. It's complex, expensive, and risky, but it tackles missions no one else can. 30 years in operation, 135 missions, a telescope, a space station, dozens of satellites. It seemed like the formula was perfected. But when the last shuttle, Atlantis, touched down in July 2011, no one had built a replacement. Orbital spaceplanes didn't vanish, they just got a lot smaller, and they stopped carrying people. Right now, in this very second, a craft is flying high above us that we know almost nothing about. It has wings, it's reusable, it flies without a pilot, and it belongs to the United States Air Force, the Boeing X-37B. It stretches about 9 meters long, with a wingspan of 4.5 meters. That's roughly a quarter the size of the Space Shuttle. A small winged vehicle that looks like a miniature space shuttle, and acts like one too. It reaches orbit, carries out missions shrouded in secrecy, and then returns to the runway, gliding in like a glider, like the shuttle, only without a crew and without live cameras. Right now, X-37B is orbiting Earth on its 7th mission. 7th. Its designation is Orbital Test Vehicle 7. This mission has been going on for nearly a year, and that's not even a record. The previous mission lasted 908 days, 2.5 years of continuous flight. What was the spacecraft doing all that time? We don't know. The Pentagon sticks to vague phrases like conducting experiments in orbit. What kind of experiments? For whom? With what results? Silence. And this is where things get really interesting. The current mission, the 7th in the series, stands apart from all the previous ones because of a single technical detail that sent analysts around the world into a frenzy. The X-37B has entered a highly elliptical orbit for the first time. What does that mean? Usually, orbital vehicles follow fairly circular paths at roughly the same altitude, but a highly elliptical orbit is more like a stretched-out ellipse. At its lowest point, the perigee, the vehicle flies about 323 kilometers above Earth. At its highest point, the apogee, it climbs almost 39,000 kilometers up. For comparison, geostationary communication satellites hang around 36,000 kilometers. So this small winged craft rises above satellites that beam television signals across entire continents, then plunges back down. Why does it need such an orbit? What kind of mission demands a path like this? No one outside a tight circle of cleared individuals knows about this, and it's that very secrecy that fuels the sense that something far more advanced lies hidden beneath the classified label, beyond what we're shown. Meanwhile, on the other side of the Pacific, something equally intriguing is unfolding. In the fall of 2023, China completed an orbital flight of its own secret reusable spaceplane. It spent 268 days in orbit, no press conferences, no publicly available photos, not a single official name. Western analysts have given it the unofficial nickname Shenlong, meaning dragon. What we do know, the craft is reusable, winged, unmanned, and launched atop a carrier rocket. Sound familiar? 2 superpowers, 2 secret winged vehicles orbiting Earth. This isn't a leftover of the Cold War anymore. It's a new race, and it's happening right now, away from public view, behind closed doors. Military spaceplanes aren't the only players here. The Dream Chaser spaceplane, a civilian project designed to deliver cargo to the International Space Station, is already built. Its body is complete, the wings are attached, and the heat shield is installed. It hasn't flown in space yet, but simply existing proves that winged orbital technology is alive and in demand beyond just the military. Here's something interesting. There's one detail that's easy to overlook amid all the secrecy and technological hype. Both the X-37B, the Chinese Shenlong, and the future Dream Chaser launched the same way, inside the nose cone of a standard carrier rocket. The X-37B flies on a Falcon Heavy or an Atlas V. The Chinese vehicle rides its own rocket. None of them take off from a runway. None climb to space using their own engines. Each one is essentially a payload, a very smart, very expensive, reusable payload, but still just cargo that the rocket pushes into orbit. You could chalk this up to strategy. Rocket launches deliver the spacecraft precisely where it needs to be, in the exact orbit, at the exact time, with the exact inclination. For military use, that makes sense. Why build a plane that takes off from a runway when a rocket does the job more reliably? But there's another explanation. The sealed cabin of a typical airliner can't withstand the harsh conditions of space. The vacuum, the temperature swings of hundreds of degrees between the shadowed and sunlit sides. The boundary between aviation and spaceflight isn't just an altitude line, it's a wall built by the laws of physics. And to break through it, every existing spaceplane still relies on a rocket. This creates a strange picture. On one hand, there's the shuttle's heroic legacy, the commercial reality of suborbital flights today, the secret future of military drones. Spaceplane technology seems to be thriving. two superpowers quietly battle over it. Private companies build their own craft. Each new mission of the X-37B lasts longer than the last, climbs higher, and tackles missions they won't disclose. It almost feels like the most advanced spaceplane was built long ago. We just don't know about it. It's probably flying somewhere out there, under the label Top Secret, doing things we can only imagine. But if the technology is really that advanced, why hasn't a single one of these vehicles mastered a simple task: accelerating to orbital speed on its own? Because 2 is not 8. That's the whole answer. The top speed of the X-15 was about 2 kilometers per second. That sounds impressive, over 6 times the speed of sound, faster than a sniper rifle bullet. But Earth's first cosmic velocity, the speed you need to reach orbit, is roughly 7.9 kilometers per second. The difference between 2 and 8 isn't just 4 times faster. It's the difference between a jump that ends with a fall and staying up there forever. The X-15 jumped beautifully, high, record-breaking, but it always fell, every single time. Let's test your intuition. Imagine it takes 1 unit of energy to speed a craft up to 2 kilometers per second. How many units would it take to reach 8 kilometers per second? 4? Kinetic energy increases with the square of velocity. Not 4 times more, 16 times more. If you guessed that, well done. If not, no worries. This mismatch between intuition and physics is exactly what fuels the illusion of progress in spaceplane development. Now let's talk about Virgin Galactic. This company promised space tourism for $250,000 per ticket. Their vehicle, VSS Unity, has never crossed the 100-kilometer Kármán line, the internationally recognized edge of space. Passengers count as space tourists only under American standards, which draw the boundary at 80 kilometers. By global standards, they technically haven't been to space. And on top of that, Unity's speed isn't even half of what the X-15 reached 6 decades ago. In simple terms, we haven't made progress. We've actually gone backward. So what about the Space Shuttle? That definitely reached orbit. It was the dream spaceplane, reusable, winged, and capable of landing on a runway like a regular airplane. But here's the catch: it couldn't take off on its own. The shuttle launched vertically, boosted by 2 solid rocket boosters and a massive external fuel tank feeding its main engines. It wasn't a single vehicle. It was a 3-part system, assembled fresh before every flight. The only reusable parts were the orbiter itself, which glided back to land like a glider, and the solid rocket boosters. They parachuted into the ocean and were recovered for refurbishment. But that giant orange tank, the one that took up the most space on the launch pad, was disposable. Every launch required a brand new tank. Every tank ended up as space junk. The shuttle's reusability was, to put it mildly, only partial. But the real nightmare wasn't cost or logistics. It lay in the sheer mass. The external tank held liquid hydrogen, the fuel, and liquid oxygen, the oxidizer. Even though the hydrogen tank was 2.5 times larger in volume, liquid oxygen made up 2/3 of the total weight of the fuel mixture. Oxygen is far heavier than hydrogen. Imagine going on a hike and realizing your backpack weighs 6 times more than your tent, food, and everything else combined. And most of that weight comes not from your gear, but from the air you decided to carry in tanks. Rockets have to haul their own air to burn, the oxidizer. Airplanes get oxygen from the atmosphere for free. Rockets pay for every gram. And here's the trade-off. Up to 90% of a modern rocket's mass is fuel. 90%. The payload, the very reason for the mission, sometimes makes up just 1% of the total weight. 1%. This isn't really a vehicle. It's a barrel of fuel with a tiny box strapped to the side carrying the cargo. The efficiency of chemical rocket engines comes down to a measure called specific impulse, and for these engines, it's painfully low. Every pound of useful payload demands 99 pounds of everything else: structure, fuel, oxidizer. The math is ruthless. All existing and in-development spaceplanes, both suborbital and orbital, relied on external launch systems. They either took off from a carrier airplane or launched vertically using rockets. None lifted off on their own. But there were attempts. The British Skylon project aimed to create an unmanned spaceplane that could take off and land horizontally, just like a regular airplane. Its standout feature was the hybrid air-breathing rocket engine called Sabre, designed to use atmospheric oxygen up to about 16 miles high, then switch over to onboard liquid oxygen. It was an elegant solution. Why carry all your oxidizer when you can breathe the air for the first half of the journey? Unfortunately, the company behind it, Reaction Engines, went bankrupt in 2023. The project shut down. Lockheed Martin proposed Venture Star, a single-stage vehicle with vertical takeoff and horizontal landing. They scrapped its smaller prototype, the X-33, back in 2001. Meanwhile, the Defense Advanced Research Projects Agency worked on the Exceed-1 concept, a two-stage system where a reusable, winged first stage would climb to a suborbital altitude, launch a single-use second stage carrying cargo, then return and land like an airplane. Boeing pulled out of the project. The whole effort shut down. Skylon, Venture Star, Exceed-1, 3 countries, 3 decades, 3 different approaches, 1 outcome. There's one clear reason. The biggest hurdle to building true single-stage-to-orbit spaceplanes is the low efficiency of existing chemical rocket engines. It's not a lack of funding, not missing political will, not secrecy. It's physics. Chemical combustion simply doesn't produce enough energy per kilogram of fuel for a vehicle to lift itself, its structure, oxidizer, and anything useful straight from Earth's surface into orbit in a single shot, unaided. Every spaceplane today is a compromise with that math. A sleek, expensive, technically refined compromise, but a compromise nonetheless. So the problem lies with the engines. But even if we develop the perfect engine, another enemy remains. An enemy we can't outrun. The planet we call home. Earth weighs 6,000 trillion kilograms. This isn't just an abstract number from a textbook. It's a sentence for every spacecraft trying to break free from its surface. Our planet's powerful gravity drives up the cost and energy needed for orbital flight. Here's the frustrating truth. Building a single-stage spaceplane to launch from the Moon or Mars, where gravity is far weaker, would be much easier. The spaceplane isn't a fantasy. It just wasn't born on the right planet. The best example is SpaceX's Starship. To break free from Earth, this ship needs a colossal booster called Super Heavy, the first stage, as tall as a 20-story building, carrying 33 engines. This massive machine exists for one purpose: to push Starship through the thickest layers of Earth's atmosphere. But that very same ship, experts calculate, can take off from Mars all on its own. No booster, no extra stages, just itself. The difference isn't in the ship. The difference is in the planet. Here we have to ask an honest question. Why do we cling so stubbornly to the idea of a spaceplane? Maybe it's because the concept is so captivating. A craft that speeds down a runway, climbs into the sky, reaches orbit, and then returns. It feels elegant. It calls to mind the flight of a bird. But Earth's gravity-well doesn't yield to elegance. Making a single-stage ascent to orbit practical might demand fundamentally different engines, nuclear propulsion systems, or ground-based laser launchers. Technologies that, for now, remain only theoretical. And yet, one attempt to defy gravity is happening right now. Radian 1 is a concept for a fully reusable orbital spaceplane that takes off and lands horizontally. Its creators know that onboard thrust alone won't be enough to accelerate from a standstill, so they came up with a solution that would have baffled engineers from the last century: a launch catapult, a rail platform over 3 kilometers long, powered by rockets. The catapult accelerates the vehicle first, then it switches on its own engines. The most energy-intensive part of the flight, the first few seconds, the heaviest burden, goes to the ground. In September 2023, The first test took place with a scaled prototype called PFV-01, a small model on rails, the first step. Will it work? We don't know. And both answers speak volumes. If Radius 1 succeeds, it means the dream of a spaceplane is still alive. It just needs a crutch in the form of a 3-kilometer-long catapult. But if it fails, then Earth's gravity really is too strong for sleek solutions. The only honest way to leave this planet is raw vertical rocket power, burning thousands of tons of fuel in minutes. We live at the bottom of a deep gravitational well. Every winged craft, every elegant horizontal takeoff design tries to escape it as if the well doesn't exist. But it does. It won't go away. And rockets, despite their wastefulness and brute force, remain the only reliable answer. And Radius 1 waits on the tracks, ready for its chance.